Yo, we're back at the workshop. In this video, we're going to be looking at this circuit I designed and built. It's a 6-stage temperature sensor hooked up to this thermopile. The thermopile feeds a string of comparators, and as you can see, when you heat it up with the flame, it will start to produce a voltage. We don't have the meter, but we will later. But you can visually see it's getting warmer and warmer as each light bulb lights up. And once you get to the 6th stage, you get a little alarm, a flasher. And then it will start to cool down. And as it cools down, the lights will turn off one by one. But it takes a while for it to cool down. But there's just one issue. I wanted the white flashing light to turn on last, but it does this weird thing where it turns on before the 6th stage, and then it starts flashing. I've tried to figure it out for a while, can't fix it. I think if we have time at the end of the video or in another video, we're gonna see why that is, but it's pretty finicky. But yeah, we're just kind of gonna explain how this whole thing works and how we built it. And so because the temperature sensor that we're using is a thermopile, we're going to explain how they work. But first, to know how a thermopile works, you need to know how a thermocouple works. So a thermocouple looks something like this. The red strip is one type of metal, and the green strip is a different type of metal. So it's essentially two metals joined together at a junction. Two different metals joined together at a junction. And I have it split down the middle into two different temperature zones. So typically, for a thermocouple, you will apply heat to this side where the junction is, and you will get a voltage on the contacts on the other end, as long as T1 and T2 are different. And we can see that in this graph as we increase our difference in temperature. In other words, as we heat up T1, the junction, our voltage out will go up. But a thermocouple produces a very small voltage, so that's why we use thermopile. It's nothing but a string of thermocouples, still divided into the two zones. And as we can see on this graph, I've illustrated that it makes more voltage by making a steeper curve. And in this case, this thermopile would produce 3 times the voltage of this thermocouple because it has 3 separate thermocouples inside. But the voltages would add up. So you'd get 1, 2, 3 times your thermocouple voltage. But a thermopile in real life will have many more strings than just 3. This is just an illustration. So now we're going to look at our thermopile and take some measurements to see that it works. But very quickly, before we test our thermopile, I just want to show you an application of thermopiles aside from this project. In this project, we're just making a generic temperature sensor, but this is a common real-life example. So this is the thermopile. It would be inside of a gas heating element, such as a fireplace. And then the output of the thermopile is these 2 wires. You would have your control switch mounted on your wall or someplace, maybe a remote. So if you close the control switch, and if the thermopile was hot, the voltage produced would allow a current. This current would flow through a solenoid inside of the gas valve. The gas valve would be this whole area. And what would happen is this solenoid, this coil of wire, would become magnetized from the current, opening up this gas valve that's normally closed by a spring, and your pressurized gas supply would work its way up to the pilot and continue to shoot out gas for the flames. And so it's a self-sustaining system. As long as the thermopile is hot, you get your current flow and you get your gas flow and you get your flames. But it's a safety thing because if the flame went out for any reason, you would not want the gas to continue shooting out because then your house could explode if it goes for long enough. So if the flame goes out, eventually the thermopile cools down, your current becomes so small, eventually zero. And then the weight of the spring is stronger than the weight of the solenoid, and the gas valve will close, and you will automatically turn off your gas. So now that we kind of had that little demo, we can actually test the thermopile. Alright, so we have our thermopile hooked up to our voltmeter. That's the output of the thermopile. We got some alligator clips going to our leads. We're on DC volts. We're reading 0 volts because it's cold, but we'll watch the voltage go up as we heat up the thermopile. I'm heating up the left side. If I heat it up in the middle, we'll produce less voltage because, again, it depends on the difference of temperature between the two sides of the device. So you can see we got like about 300 millivolts. It will continue to go up. Typically, I think this one will go to like 600 millivolts. But yeah, you can see it's functional. And now as I take the flame off, you can see as it cools down, the voltage produced goes down as well. So now we can see how we're going to measure this and put it in a circuit so that we can get our indicators. So for our 6 stages, we have 2 greens, 2 yellows, 2 reds, and then the white, which is the same as the last red. And so we've decided we want our 6 stages to be approximately 25 millivolt steps. So every time the thermopile goes up 25 millivolts, an additional light bulb will turn on. And how we're going to do this is with a voltage divider. So it looks complicated, but it's not. We have our 12.6 volt source. It's going straight through 7 resistors, straight to ground. So the resistors we've selected, starting from the bottom, are 1, 2, 3, 4, 5, 6, are 680 ohms each. Our 7 at the top is 330,000 ohms. And this voltage divider will give us 6 taps in the circuit, all at different voltage levels, hopefully 25 millivolts apart each. And how we picked these values is as follows. So the first step is to determine your current, and that's easy. You just take your total voltage, 12.6, divided by the total resistance. So 330,000 plus 6 times 680, 334,080 ohms, gives you this many amps, which rounds up to about 37.7 microamps. So you'd get about 37.7 microamps flowing down here. We're not able to measure that, but we will be able to measure our voltages to verify. Now we're going to start with the V1 because it's at the bottom, it's the easiest. We want it to be about 25 millivolts, so all we have to do is take our current and multiply it by this resistor. That will be the voltage across this resistor. So V1 here is equal to VR1, which is equal to the current times R1. So we got our current multiplied by 680 ohms. You get approximately 25 millivolts. So that's your voltage here. So this point will be 25 millivolts above ground, because the only thing separating it from ground is this resistor with this current. And then for V2 it's easier. You can just double this voltage, because you know the voltage across each of these 680 ohm resistors will be the same. So as you keep getting more resistors away from ground, you keep getting more voltage. So each step is 25.6 millivolts apart. So these are the voltages that we're calculating we're going to get on this voltage divider. And we can see at the very top we have 153 millivolts, which means this 330k ohm resistor at the top is dropping almost the entire 12.6 volts. We're only getting a tiny amount of voltage across each of the 680 ohm resistors. And so our last red light bulb will turn on and the alarm will go off at 153.6 millivolts of the thermopile. And so now we can measure that. We have our circuit hooked up to the 12.6 volt battery. It's not exactly 12.6 volts, and the resistors have a little bit of tolerance, I believe 5%. So we're not going to get exactly 25 millivolts per stage, but we have our black lead hooked up to ground, and so wherever we touch our red lead, we'll get our voltage at that point. So we're going to start with V1. This is the last in the resistor chain. You get about 30 millivolts, so it's quite a bit off. But then you go to the next point in the chain, which is right here. You can see 54.4 millivolts. That's pretty close to 51.2. Go to the next one. 79.4 against 76.8 that we wanted. The next one, get 104.3. That's 102.4 we guessed. The next one, 128.9. We figured 128. And then the last one in the stage, between the 330 ohm resistor and positive, is 153.8 millivolts, which is very close to what we guessed. And then this 330 ohm resistor just goes up to our supply, which is 12.4 volts. So we can see how it works. We have the resistor chain going kind of in this direction, from ground to positive. And they're hooked up to these devices, which we'll talk about in the next section. But yeah, so this is how we made a 6-stage kind of temperature indicator. And now we're going to see how we can make this more useful. So it's great that we have these 6 tap voltages. Those are our reference voltages. But now we have to see what that has to do with the thermopile. So we're going to connect it as shown. Our thermopile here, going into this component, which is an operational amplifier. That's these 3 black chips on the board. Each one has 2 op amps in it, for a total of 6. But this circuit represents one single stage. So we're going to use the first stage as the example. So we have our 25 millivolt tap, so V1 input voltage, and we have our thermopile voltage going into the op amp. And for an op amp, we can see we have an output not connected to either of the inputs. And in this case, it acts as a comparator. So what that means is if the positive input is higher than the negative input, the output will turn on all the way up to 12.6 volts. If the positive input is lower than the negative input, the output will turn off all the way down to 0 volts. So if the thermopile voltage goes above our reference at 25 millivolts, we get 12.6 volts here, and the green LED number 1 will turn on. If the thermopile voltage is lower than 25 millivolts, the output will turn off, and our green LED will turn off. And so here's what it would look like with all the stages connected. We have our voltage divider with our 6 tap voltages. Those are the negative inputs of all the op amps. All the positive inputs of the op amps are hooked up directly to the thermopile voltage. So what will happen is the thermopile voltage will go up. It'll hit 25, and this one will turn on. When it goes up to 50, this one will turn on as well. That's your 2 green lights. Then you got your 2 orange and your 2 reds. When it goes all the way up to 150 millivolts, all the lights will be on. And that's how that works. And that's what we have on the board here. You're ignoring this section on the left, but these 3 components and these 6 LEDs. Yeah, so that's why you can use comparators, operational amplifiers, to indicate temperature of a thermopile. It's kind of an arbitrary experiment, but you could do lots of things. In the next video, we're going to explore the second half of the circuit, which is that alarm but the video has to be less than 15 minutes, so bye.